Right, so look into it. In this topic, right, we need to figure out, mainly three differences of a solution. So solutions mainly are categorized into three kinds: true solutions, colloidal solutions, and suspensions. See, if at all we have a homogeneous mixture of solute and solvent, then we say it is a true solution. Okay. In true solutions, there will not be any visible boundary. You will not be able to see any boundary between the solution, which means if you have a solution here, you will not be able to differentiate between solute and solvent particles just by watching it. Got it? Here. So it will be completely transparent solution. While colloidal solutions are heterogeneous, heterogeneous means there will be some phase boundary across the particles. For example, if this is a solute particle and the other one is a solvent particle, so there is a visible boundary between these two. So therefore, that is heterogeneous form. So heterogeneous, but it is uniform. That means it will be uniformly distributed. Density across the solution will be same. So there is a visible phase boundary, and usually colloids are colored. So may it be blood, milk, paints, cheese, butter. These are all various types of colloids. Then we have suspensions. Suspensions are heterogeneous and also non-uniform. So that means their size is so big that it will sediment. That means it will settle down in the bottom of the solution. Okay. So those are suspensions. Now, in this topic, our main idea is to learn about true solutions. Okay. Now, in true solutions, we will have different types, different classifications based on how many number of components we have. In case if you have two components, which means one solute, one solvent, we call it as a binary solution. If you have two solutes and one solvent, we call it as ternary. If you have three solutes and one solvent, it is quaternary. The idea is always solvent is only one. Solutes can keep differing. Okay. So normally, in case if you have solute, I mean, how many different types of true solutions you can make, that depends upon what kind of a combination you are taking. For example, if these are all the solvent combinations and these are all the solute combinations, these are all various forms of solutions we can get. Of course, some of these are colloids, some of them are true solutions. Okay, we will be discussing much more in detail about these uh, parts in surface chemistry. Okay, got it. So because major of them are in uh, colloidal form. Especially if you notice solid in liquid here, this part is one which we'll be reading a lot in this topic, where something like a salt or a sugar is added to water, it will be a true solution. Got it? Same is the case. If you take ethanol in water or water in ethanol, it will form true solutions. Okay. If you have any aerated drinks where gas is being added to liquid, it can also form true solutions. Okay, like aerated sodas and drinks, these are all true solutions. Solid and solid mixed together, these are all alloys. Okay, so they are also forming true solutions here. So you can see these are all the examples of true solutions. Next. Generally, whenever we refer to solute, we expect this to be a smaller quantity. Solvent is the one which is in larger quantity or bulk in quantity. Okay, just a second. Yeah. Check. When it comes to solutions, true solutions, one important aspect we need to learn is about the strength of the solution. Okay, what is the strength of the solution? So you can see, to understand the strength, we have various parameters. One is mole fraction, molality, percentage weight by weight, those kind. Check out. Mole fraction is number of moles of solute by total number of moles. Molarity is number of moles of solute by volume of the solution. Okay, so number of moles of solute by volume of the solution in liters. Molality also we came across the definition, number of moles of solute by weight of the solvent in kgs. And then percentage weight by weight. This is percentage compositions where we are talking about weight of solute by weight of solution into 100. Same goes with percentage weight by volume. Okay, and these two are another important terms which you need to be always remembering. I mean, this is all something which we learned in mole concept already. Molarity is percentage weight by weight into T, which is density of solution, into 10 by molar mass of the solute. Molality, on the other hand, is 1000 times of molarity divided by 1000 times of density minus molarity into molecular weight of solute. Okay, now molarity and mole fraction, how they are related, let's see. In case if we talk about definition wise, molality is number of moles of solute by weight of solvent in kgs. Okay, while I can say mole fraction of solute is number of moles of solute by number of moles of solute plus number of moles of solvent. This is when it comes to mole fraction. Okay, now I can actually write the mole fraction in this form. So 1 by xs will be equal to ns plus n of solvent by ns, which is equal to 1 plus number of moles of solvent by number of moles of solute. So that is number of moles of solvent by number of moles of solute is equal to 1 by xs minus 1. Okay, 1 second. So 1 by xs minus 1. So you can see, write this as number of moles of solvent by number of moles of solute is equal to 1 minus xs by xs. Now if at all I reverse this, I will get this as number of moles of solute by number of moles of solvent, which is equal to xs by 1 minus xs. Okay. Now number of moles of solvent, we can write it as, you know, weight of solvent, correct, which is normally in grams here, right, divided by molar mass of the solvent, that is equal to xs by 1 minus xs, which implies number of moles of solute by, now this is in grams, so if at all I have to convert that into kgs, I have to divide it by 1000. So if I divide it by 1000, all right, so this is what I'll be getting into molar mass of solvent, correct? Sorry, not divide, multiply, because I have to represent that in kgs, right? Solvent in kgs into 1000, that into molar mass of solvent, which is equal to xs by 1 minus xs. Now you can see this fits into the definition of molality. So molality is equal to 1000 times of xs by 1 minus xs into molecular weight of solvent. Okay, so this is the way you can relate it. Clear, everybody? Please check it out. This is a relation between molality and mole fraction. Okay, so you can write the same equation in terms of xs also. But depending upon whatever the question is asked, you should know how to represent or how to change one particular unit to the other. We also know the relation between molarity and molality. Okay, so molarity, capital M, and molality, small m. Since we already derived this in the mole concept and we use it just often as a formula, we can directly take the formula that molality is equal to 1000 times of molarity by 1000 times of density minus molarity into molecular weight of solute. Okay, so this is the formula which we often use, where D is the density of solution, density of liquid solution. Okay, and unit wise, if you notice, unit wise, molarity is always represented in mole per liter. Molality is represented as mole per kg, correct? Percentage weight by volume is represented in grams per ml. Okay, so any representation of the amount of solute, either in terms of grams, moles, and how much it is present in the solution, correct, or how much it is present in the solvent, this measures the strength of the solution. Got it? And also known as the concentration of the solution. So concentration or the strength represent the same thing. It is basically showing us that how much amount of solute is present. Got it? So I would, if you haven't made a note, please check it out how exactly it is to be done. By the way, already uploaded the pre-notes. Correct? You can have a print next by next class. Meanwhile, you can have a small note here and there wherever it is required. Just note the formulas here. All right. So you can see molality versus mole fraction, and here molality versus molarity. Okay. Sorry. Let's learn more into the details of it. This topic is more about mixing of two liquids. When you mix two liquids, what are the important parameters that you should look out for? One is, what is its volatility and what is the vapor pressure of that liquid. See, when I use the word volatile, which means we expect that the liquid evaporates at room temperature. Okay, it is just a surface phenomena where the surface particles of a certain component will start evaporating on its own at its room temperature. Got it? Why would that happen? The surface particles which are maintained at a different temperature T1, and outside there is a temperature T2, correct? So between these two, there will be an exchange of heat that happens, and the surface particles will gain that energy and try to evaporate and try to come out of the particle. So this evaporation at room temperature is called as volatility, and we call the liquids are volatile liquids. For example, water. Water evaporates at room temperature, so we say it is a volatile liquid. Okay. Now, if I keep any lid over it and make it into a closed container, still the phenomena keeps happening. Evaporation will keep happening, but slowly the vapor particles will get accumulated also here. And as the vapor particles accumulate, you will notice a new phenomena will start now. Slowly, some of the particles will start getting into the liquid, and this phenomena is called condensation. So vapors will start to condense. So you will see a certain time, you will see after a certain time, evaporation and condensation. Both of them are happening, and both of them are happening simultaneously. Okay, both of them are happening simultaneously. And you can see at equilibrium, rate of evaporation is equal to rate of condensation. Got it? At equilibrium, you'll notice that rate of evaporation is always equal to rate of condensation. Next, you see, when it comes to a term called vapor pressure of liquid, what does this mean? Let's see. It is the pressure that is exerted by the vapors which are at equilibrium on the surface of the liquid. Got it? At that given temperature, right? Then how much amount of pressure it is exerting is what we call it as the vapor pressure of the liquid. Got it? Now, can I say that at a saturated solution, which means when the rate of evaporation and rate of condensation is happening same, then the number of particles in this particular space will be constant. So over a period of time, it will apply a same amount of pressure, isn't it? So the time at which this equilibrium reached, that is the equilibrium time, and at this position you can see the rate of evaporation and condensation becomes equal. At this situation, how much amount of pressure it is applied on the liquid surface is called as the vapor pressure of the liquid. Okay. Now, vapor pressure of a liquid depends upon what all factors you see. Vapor pressure depends upon escaping tendency of the liquid molecule, that is how easily they can escape to the surface. Correct. Second, they also depend upon the volatility of the liquids. Okay. So that means if the liquids have weak affinity between them, they will be relatively more volatile. And more importantly, vapor pressure only changes with respect to temperature. Correct. So when the temperature changes, vapor pressure will also change. Correct. So vapor pressure is always subject to change in temperature. Okay. So now you notice this one. Suppose if I am operating at a constant temperature T1, then there will always be some amount of molecules that are evaporated. So this will be number of particles, right? Sorry. This is how many particles present in the liquid. Okay. There will always be some movement, random movement in the liquid also, just like gases. There will be random movement of liquid particles also. So liquid particles are randomly moving like this. And as the particles keep moving, we can say every particle has different speeds, right? So we can say the number of particles which have similar speed with respect to the total number of particles, that is a fraction of particles which are showing a particular speed like this, right? So this one. This is exactly like Maxwell-Boltzmann's curve, right? Now notice there will be certain threshold velocity of the particles. Beyond that, if the particle starts gaining the speed, it can escape out of the liquid and come out into vapors. Okay. So wherever you see the escape velocity, I mean, this is the threshold velocity. If it crosses, we can expect that those particles will be mostly in the uh, vapor state. They'll get into the vapor state. Clear? Now, if you may recall, Van 't equation, that is, suppose uh, at equilibrium, let's say water itself is a volatile liquid. I'm taking an example of water. Water will be in equilibrium this way, liquid and gas. Then we know that if there is an equilibrium existing, that will be Kp, and Kp will be equal to partial pressure of H2O liquid. Okay. You know that Van 't equation. As per Van 't equation, we learned that okay, uh, log of K2 by K1 is equal to delta H by 2.303 into 1 by T1 minus 1 by T2. This is what we learned, that at I mean at equilibrium, uh, if the temperature is changed, then the Kp value changes. And how they are related? This is the way they are related. That is called Van 't equation. So this is Van 't equation. Got it? Now, can I say that at temperature T1, if pressure of water, that is vapor pressure of water, is P1, and at temperature T2, if vapor pressure of water is P2, I can substitute these values here because Kp will be same as the pressure. Hence, we can write that here as ln P2 by log of P2 by P1 is equal to delta H of vaporization, because this particular form of enthalpy where liquid is converting into gas at equilibrium is called as vaporization. Delta H of vaporization by 2.303 R into 1 by T1 minus 1 by T2. The same Van 't Hoff's equation is now modified. Got it? So this modified equation is what we call it as Clausius Clapeyron's equation. So it is a modified equation. You can write this P1 and P2 as vapor pressures also. That is log of vapor pressure 1 by, sorry, this is P2 by P1, my mistake. This is P2 by P1. Okay. So I can write this as vapor pressure 2 by vapor pressure 1 is equal to delta H of vaporization by 2.303 R. 1 second. So log of vapor pressure 2 by vapor pressure 1 is equal to delta H of vaporization, this into 1 by T1 minus 1 by T2. So same equation can be written in terms of vapor pressures. Got it? Now, if you may recall that we also learned that log of Kp used to be written as delta H of reaction by 2.303 RT plus delta S of the reaction by 2.303 R. Okay, this was the original original equation at a temperature T. And when you take it at T1 and T2, you will have respectively K2 and K1 and K2 values. Implies the same thing when you write it for liquid solutions. We can write log of vapor pressure of the liquid is equal to delta H of reaction by 2.303 RT plus delta S of the, sorry, not reaction, vaporization, and delta S of vaporization by 2.303 R. Okay. So this is another equation which we can represent. So basically this is the same equation. Uh, if we plot this, let's say, if at all I plot this here, that is how does this equation go? That is log of, P versus V, P versus T. How the pressure versus temperature changes. You can see that normally this is how the graph goes. Okay. And after certain time, this is how it decreases. So here, this is the equilibrium. This side of the part is completely, you know, in liquid state, and this side of the part, it is completely in gaseous state. This is in gaseous state. Okay, so if you use this equation and plot vapor pressure versus temperature or pressure versus temperature, then this is the type of graph you will get. Okay, the point where it is changing here, correct? So this is called the melting point, and sorry, not melting point, um, this one is the triple point, sorry, triple point. And if you see, in case if you have a particular pressure, typically if pressure is 1 atm or 1 bar, the pressure is 1 bar, correct? And then if you find out a certain temperature at which liquid and gas are at equilibrium, that will become the boiling point of the liquid. Okay, so this is how typically how the graph looks like. So please check how to represent Clausius-Clapeyrion's equation and so on. And while solving this, you need to keep in mind that delta H of vaporization and delta S of vaporization are independent of temperature. Independent of temperature. Okay. So which means if at all I differentiate this, I'll write it like this. Dou by dou T of, vapor pressure, correct? Or simply, let me write on this as pressure here. ln P. ln P. That will be equal to, this will become 0 because this can't be differentiated. So here it will become minus delta H of vaporization by RT square. Okay. So this is actually another representation of Clausius-Clapeyrion's equation. Okay. Everyone clear on that? Right. So now notice this one. Suppose when it comes to liquids which are mixed, like one can act like solute, the other one can act like solvent. In that case, let us try to discuss more about the type of interactions it takes place. So let me show you. Okay, type of interactions. Type of interactions. Okay, so you can see for a solute and solvent. Okay, solute. Let's assume this as A. Solvent. Let's assume this as B. Okay, one I'll call it as solute, the other one I'll call it as solvent. Okay, so before mixing, before mixing the solutions, before mixing the components, before mixing components, okay, solute A, solute A has interactions, interactions like A type of interactions. This is called A type of interactions. Similarly, I can use the terminology for solvent also. So when it comes to solvent, it will be B. So it will be solvent B. Solvent B has interactions like B, and B type of interactions. Okay. After mixing, this is before mixing. Okay. After mixing the components, now we will have three type of interactions. Three type of interactions. One is A type of interactions, B, B, B type of interactions, and lastly AB, and AB type of interactions. So you can see these are the type of interactions which you will gain. Okay, these are called solute interactions. These are solvent interactions, and these are solute solvent interactions. Okay, and especially in solution you will find all three type of interactions happening. Got it? Now let me put you through a definition called ideal solution. Ideal solution. Correct. Ideal solution is the one when A type of interactions, BB type of interactions and AB type of interactions are equal in magnitude. So that means whatever the force of attraction which AA has, BB has, and AB has, all should be same. Correct? Usually, where do you see this more often? See, when the molecular structure is very similar, like this. Benzene and toluene are very close. CCl4, CBr4 liquid, CHCl3, CHBr3 liquid, C2H5Cl, C2H5Br will have very similar interactions. Got it? Hexane and heptane, which are very close to each other in terms of their molecular weight also, as well as the nature of the molecule also. These kind of solutions, which have very very similar to each other, correct? They will have same interactions. Okay, what I meant to say is, like for example, chloroform in its own liquid, bromoform in its own liquid will have some interactions, and those interactions will be similar even after mixing both of them. So even after mixing, if you find the same type of solution, same type of interactions, then we say they are ideal solutions. Hey guys, I hope you understood. Okay, so you can see I've written that here. So these are all the type of interactions which we have. All right. Now let's understand what are non-ideal solutions. See, if at all we have AA interaction, BB interaction, and AB interaction, but they are not same in magnitude, then we say they are real solutions or non-ideal solutions. All right. First, we will try to figure out, what all parameters we can derive, what are the types of equations we can derive for ideal solutions, and then we can apply the same for real solutions also. First thing we learn is about Raoult's law. Raoult's law is only valid for ideal solutions. It is only valid for ideal solutions. Okay. And we are only talking about binary solutions, which means one solute, one solvent. And both liquid must be volatile. These are the basic conditions for Raoult's law. Most important condition is they should be ideal solutions. That means the interactions between AA type, BB type, and AB type should be same. Okay. Then, if XA represents mole fraction of liquid A, XB represent mole fraction in liquid B, okay, of liquid B in the solution, and PA, P naught A represent the vapor pressure of the pure liquid A, or P naught B is the vapor pressure of pure liquid B, right? Then PA and PP are vapor pressure of the liquid in a mixture. This is before adding in the mixture. This is after adding to the mixture. I mean, after making a mixture. Okay. Everybody understood the terms here. Please notice this. XA and XB are mole fractions of A and B in the mixture. Okay. When you mix two liquids. PA and PB are their partial pressures. Partial pressures or vapor pressure in the gaseous state. Okay. In the vapor state. And P naught A, P naught B are the vapor pressures of pure liquid A and pure liquid B. Clear? Next, notice this one. If this is the surface of a liquid, imagine, and this is when it is only solute. When you have only solute, then let's say these are all the surface particles we have of A kind. And when you have only pure liquid B, then these are all their surface particles. Now, after mixing both of them, you will notice the interaction will happen between them. And because of the uniform distribution, you will always have one solute, solvent, this kind of, layering here on the surface. So now it is a solution with A and B. You can notice as long as this surface area is fixed for the same surface area here, okay, I mean, once I take this liquid, once I take this liquid, once I take this liquid in the same container, or you can say same surface area if you are measuring. In that case, P naught A here versus P naught A here in the third case, or P naught B here in the second case versus P naught B in the third case. If you compare these, you will definitely notice that P naught A was higher than PA and P naught B is higher than PB. Okay, because as the other solute as also occupying the surface in the mixture, it will make it less available for evaporation. Hence, according to Raoult's law, vapor pressure of any component will be proportional to its mole fraction in liquid state. So you can see Pa, partial pressure of A, is directly proportional to mole fraction of the liquid, mole fraction of A present in the liquid state. Similarly, Pb is proportional to mole fraction of B present in the liquid state. And if I remove the proportionality here, what would I get? I will get a constant, and that constant was found out to be P naught A XA. Similarly, PB will be equal to P naught B XB. So this is the partial pressure representation in terms of P naught A and P naught B. And you know that at a particular temperature, these two values are constant values. That will not change. And we are not changing the temperature and doing anything in Raoult's law. At a constant temperature, we are trying to figure out how does the pressure varies in a mixture. Okay. So now, since this is the case, we can say the total amount of pressure here, P total, which is accumulated here, will be equal to PA plus BP as per Dalton's law. And PA we learned this as P naught A XA, and PB we learned this as P naught B XB. So this will be the total pressure. So total pressure formula will be equal to P naught A XA plus P naught B XB. And we can also write this as P naught A XA plus P naught B into 1 minus XA. And if I add both of them, we'll get this as P naught A plus, sorry, P naught A XA minus P naught B XA, correct, plus P naught B. Okay, so this is what you will get it as total pressure. Done. So which is equal to P naught A minus P naught B into XA plus P naught B. This is equal to P total. Okay. Now, what if we want to plot them individually? You see, we know that PA is equal to P naught A XA, and we know that PB is equal to P naught B XB. Now notice this one. From here, if I write P naught A on y-axis and XA on the x-axis, this is y is equal to mx type of graph. So it is equation of a straight line passing through origin. Similarly, I will write this x direction here now. Just for the reference, I'm writing it this direction, not in this direction. So in that case, from 0 towards, this one, this is the graph will vary. Okay. So PB is equal to P naught B into XB, correct? And this is equal to PA is equal to P naught A into XA. Now notice one thing, this graph and this graph are two different graphs, but we can merge them. How when XA is equal to 0, that means when there is no XA, which means it is pure B. When it is pure B, then XB should be equal to 1. And when XA equal to 1, XB has to be 0. So which means this point and this point can be same, and this point and this point can be same. So that's why we merge these two graphs. So after merging, you will get this new graph here. So wherein XA is equal to 0, XA is equal to 1 is the mole fraction of A. XB equal to 1 and XB equal to 0 is the mole fraction of B. And we notice that this was that y is equal to mx straight line equation for this, and y is equal to mx is the straight line equation for this one. And now If I add both of them, this line will give you total pressure. So total pressure is PA plus BP. Okay. So this is the total pressure line, everybody. Okay. And next, you notice that XA equal to 0, XB equal to 1, or XA equal to 1 and XB equal to 0. This is what you have. And at this point O, correct, you can see both of them will meet with each other. Okay. What is the point where they are meeting here? The point where they are meeting suggests that their mole fractions are same. So you can say at this point mole fraction of pressures are same. So the pressure of A is equal to pressure of B at this point. Okay. And now notice this one. What is point A? Point A is the total pressure of the mixture, correct? When composition of the liquid A is this one and composition of the liquid B is this much. This much is the composition of B. And you know that this point C represents partial pressure of B and point B represent partial pressure of A. And you know that total pressure is always equal to partial pressure of A plus partial pressure of B. So total pressure here is AD, total distance, that should equal to BD and plus CD. So this is a relation of the length here. Okay. So this magnitude should be same as this one plus this one. Clear? So please go through it once quickly. Then we can go ahead and discuss further about the solving. So this is Raoult's law, everyone. Now you can see if we have a mixture A and B and the respective mole fractions are XA and XB, considering both of them are volatile, they will have some vapors above them and their partial pressure is PA and partial pressure is PB. This is how much we learned. But these partial pressures can also be expressed in terms of their mole fraction in vapor state because A and B are also becoming a mixture in the vapor. And in that mixture, let's say the mole fraction of A is Ya and mole fraction of B is Yb. So in case if you have Ya and Yb, then what will be the partial pressure here? So you can see total pressure. Total pressure is equal to partial pressure of A plus partial pressure of B. And partial pressure of A is, mole fraction of A into total pressure. And partial pressure of B is mole fraction of B into total pressure. Where did we learn this from? From Dalton's law. From Dalton's law of partial pressures. We learned this in gaseous state that when you have mixture of two gases, the total pressure will always be equal to sum of those two, and partial pressure can be represented as mole fraction into total pressure. Okay. Because we are talking only about binary solutions, for binary solutions, we know that XA plus XB is equal to 1, and similarly Ya plus Yb will also be equal to 1. Mole fractions will always be equal to 1. Okay. Let's use this to our advantage. We can write this as partial pressure of A, which can be written as P naught A XA as per Raoult's law, and which can also be written as Ya into P total as per Dalton's law. Similarly, PB can be written as P naught B XB, which can also be written as, YB into P total. Okay. If I write XA here, that is equal to YA P total by P naught A, and XB here as YB P total by P naught B. If I add both of them, XA plus XB, I should be always getting it as 1, which is YA by P naught A into P total plus YB by P naught B into P total must be equal to 1. So if I take that 1 to the other side, I'll get this new equation. 1 by Pt is equal to Ya by P naught A plus YB by P naught B. Correct? So this is another representation of total pressure equation in terms of mole fractions of the liquid state. Sorry, vapor state. These are the mole fractions of the vapor state. Okay, clear? Mole fractions of the vapor state. Now look into this. You know that how we plotted PT, correct? P total is equal to P naught A XA plus P naught B XB. This is as per uh, Raoult's law. And this was the line which we learned, right? This is the line which represents total pressure. Correct. This is a line which represents total pressure. Now, what if I plot the same thing with respect to mole fraction of the vapor state? Then where would it appear? So this is where it appears, correct? This is how the graph appears when you draw the same thing in terms of mole fractions in the vapor state. Okay. So this is total pressure in terms of liquid state mole fractions. This curve is in terms of mole fraction of the vapor state. What it meant, let's say I'm talking about a point A here. Point A is nothing but mole fraction of A, correct? Mole fraction of A. At some point, this is the mole fraction of A. Now, if this is the mole fraction of A, respect to that, what is the total pressure it is exhibiting? Let's say P total is the total pressure. Now, let's see where does this total pressure line goes and intersect on this graph, on this curve. It intersect here. So if you go down here, now this will become YA, which is the mole fraction in the vapor state. So when XA is the mole fraction in the liquid state, then YA will be the mole fraction in the vapor state. Okay. Mathematically, you know how to relate them. Mathematically, we know how to relate them. And graphically, now you know how to relate them. Okay. So you just make a horizontal line across this particular two curves. One is this total pressure curve in terms of liquid state. This is in terms of vapor state. If I draw a horizontal line, then those 2 points where it is interacting, those are the respective mole fractions in liquid state as well as in vapor state. Are you guys clear with it? Now, before going into further details, I want you to understand one thing, how this total pressure and external pressure works, everybody. Okay. So let me just give you a briefing on that. Okay. Orally, just try to listen to it and uh, try to relate it. Suppose if you take a glass of water right now and keep in front of you open, okay, you will have certain level of water, right? And now, after an hour, you come back. Don't expect that there is hardly any temperature change in the room. So imagine there is no temperature change in the room. And after an hour, if you come back and notice that uh, level of water in the glass, would you see any change, everybody? Will you see any noticeable change? There might be a change happening, but that is extremely low, isn't it? This is what I meant. So if you take glass of water like this, okay, and you come back and notice it here after 1 hour, it still look the same. The level hardly changes. Which means, does that mean there is no evaporation happening? Does that mean the liquid is not volatile? Well, here liquid is volatile. It is happening and it is happening very slowly. It's happening very slowly. It is so slow that there is hardly any noticeable change you can see. You will not be able to identify any noticeable change. Okay, right. So check. Since there is no noticeable change here, correct? What if I start heating this liquid now? That is water. If I start heating that liquid, you take the glass and start heating it. And let's say after some time, now the temperature currently is now at almost 99 degrees Celsius, around 99 degrees Celsius after heating. Okay, you increase the temperature. This is the new temperature of the liquid. Now I can say at this particular temperature, you will see the particles will start moving more often. It will go a little faster, start going up. Okay, you'll see some vapors accumulating, and the level of this will start decreasing here. So you will notice that this is how the level will come, and this is how it appears. Clear? Okay, do you understand that? Now, why is that earlier there is hardly any noticeable change? Now it is a large amount of noticeable change appearing because you are very close to the boiling point. When you are very close to the boiling point, you will start seeing there is a drastic movement of particles into vapor state. Got it? So once it reaches equilibrium, that means the vapor state and liquid state will have equal amount of vapor pressure, or I would say, uh, sorry, the vapor pressure of the liquid and the atmospheric pressure are equal. Then we say the liquid is boiling, correct? And this is the exact point, everybody. This is that exact point. So this point A represent the boiling point of that liquid. And at that boiling point, what is the pressure it is operating? Okay. So this will be the same as the external pressure. So if you calculate this, that means it is same as external pressure. Or if you know the external pressure, that will be the same amount of pressure here, and you push it back here, and you will be able to see what is the mole fraction of liquid in the liquid state, mole fraction of the component in the liquid state. Okay, everyone. So for that A, for this A here, correct? At this point A, if XA is the mole fraction in the liquid state here, then respectively YA will be the mole fraction in the vapor state, which is this one. So this will be the mole fraction, everyone. Clear? So I hope you guys understood what is XA and YA now. So YA initially you'll hardly notice because there are hardly any vapors above, correct? If you want to see the YA amount actually available, you should always see only after this point B. Now, what is this point B? This is the point B where the first bubble is forming. This is the point where the first bubble is forming. That means it is very close to 99 degrees or 98 degrees, something like that, very close to boiling point. So this is that temperature. At that temperature, you will see the first bubble forming, right? So you'll be small bubbles coming out. So small amount of vapor, small amount of vapor quantity is observed. Okay. So at that vapor quantity, you will not be able to noticeably see any mole fraction difference. But as you move towards 100 degrees here, 100 degrees of water, suddenly or drastically, you will see lot of water content decreases and everything will be in the vapor state. There will be small amount present in the liquid state, correct? But everything will be appearing in the vapor state. Clear, everybody? So from here, we can say that when you are at point A, if the atmospheric pressure is at point C, that means if the atmospheric pressure is very high, let's say outside atmospheric pressure is 1 atm and the vapor pressure at 25 degrees for water is maybe zero point 0.1 atm. So that means this P atm is very high. At that point, you will hardly find any vapor. Everything will be in liquid state. Okay. So this is that point C, everybody. This is like the point C where everything is in vapor state. Clear? Now, if you come over to the point B here, right? Sorry, not point B, my mistake. Let me put one more point here somewhere close to this one. Okay, I'll write it as E, point E. Point E is somewhere here, everybody. That is very close to that of boiling point. Okay, where some bubble is just started. Or we can say exactly at A, there is a lot of bubbling that is happening. Got it? At point A, a lot of bubbling that is happening. When the bubbling happens largely, and then you can see this pressure and the external pressure matches. Now, if the external pressure is this much and it is matching the total pressure of the vapor state, I meant to say now the vapor pressure the atmospheric pressure have decreased from 1 atm to zero point 0.1 atm. Then the vapor pressure of the liquid as well as the external pressure is same. That means you have reached to this point. Now a lot of bubbling will happen. And if you decrease the pressure further, if the external pressure is further decreased and you reach to point B, now in the liquid, hardly anything will left. Only one droplet will be left. Rest all everything has evaporated. So this is the point where there is only one drop in the liquid. Rest everything is in vapors. And if you come towards point D, everything is in vapors. There is no more liquid available. Hence, the green area is basically representing if the external pressure is in this region, the component is always in the vapor state. If the external pressure is in this region, the component is always in liquid state. And when the external pressure is in this region here, correct, which is coinciding the points, coinciding this line here, then that means you are at the boiling points. Okay. So this particular uh, area in the graph where it is differentiating a pure liquid state versus a pure vapor state, that is called as vapor liquid equilibrium area. So this yellow space is called VLE, vapor liquid equilibrium. A is called as the bubble point, where it is noticeably the first bubble formation. B is called as the dew point, where we are seeing every liquid is converting into vapor except a drop present. Clear, everybody? So please understand the graph carefully, what exactly the states are. What happens if your external pressure overpowers your vapor pressure or if it is less than the vapor pressure? Remember, if P ATM is greater than, atmospheric pressure is greater than total vapor pressure, majority of the content will be in the liquid state only. If P external pressure is less than, right, the vapor pressure of the mixture, then it will be completely in vapor state. If it is equal, it will be in the VLE, vapor liquid equilibrium. Okay, please go through it once quickly, then we'll discuss it with a question. So you got to assume that heptane and octane are ideal solution. Sorry, ideal solution. This forms an ideal solution. And at 373, the P naught A and P naught B are mentioned. Let's say A is heptane, B is octane. We need to find out P total of the mixture when we are mixing 26 grams of A and 35 grams of B. So let's see how we can do it. So number of moles of A is 26 by the molar mass of A. Number of moles of B is 35 upon the molar mass of B. Okay. So see what is the molar mass here. So molar mass of heptane is 100. So 26 by 100. And this is 35 by 114. Okay. So after solving, this is 0.26 and after solving this, I'm getting it as 0.307. Then you calculate the mole fraction of A, which is 0.26 upon 0.26 plus 0.307. If I put that value, it's coming out to be 0.458. 0.458. So then I can say that XB will be simply 1 minus XA, which is equal to 0.542. Okay, so the total pressure will be equal to 105 into 0.458 plus 46.8, which are these P naught A and P naught B values, that multiplied by 0.542. So check the values given, correct? So if I add both of them, it is coming out to be 73.5 kilopascals. Okay, so you should notice that P total will always be between PA and PB. The value should always be between P and PB value. P naught, sorry, P naught A and P naught B value. Okay, so this is how you calculate the total pressure. I guess this is clear, everyone. Now, let me show you what are all the properties of ideal gas, ideal solution. Okay, if you claim something is an ideal solution, then the first thing you should know is that their interactions are same, whether it is AA interaction, BB interaction, or AB interaction. All the type of interaction should be similar, right? Second, it obeys Raoult's law. If it's an ideal solution, it must obey Raoult's law. That is, Pt is equal to P naught A XA plus P naught B XB. Okay. And next, delta H of the mixing. That is, how much amount of enthalpy change in the mixing observed, that has to be zero if it is ideal solution. So there should not be any energy released or energy absorbed during the mixing of the solution. And because there is no energy released or absorbed, there should not be any change in the total volume as well. So total volume should be same as the volume of individual solute and solvents. So Va plus Vb. So V solution minus Va plus Vb should be always equal to 0. Now, it's like this. If you have, let's say if you have a container here and another container here, A and B. Now, both of them are mixed and made into a large container of volume Va plus Vb, correct? In that case, now can I say that the solute particles of A in mixture and solvent particles of B in mixture, both will have more space to move around. And since it will have more space to move around, now we can say the delta S of the mixing, that is total entropy change, is always increasing. As the overall volume is greater, then the volume of the particles in the liquid state of A as well as B, both will increase their entropy. And you know that delta H of mixing is 0 and this is positive, which makes delta G of the mixing negative. So our ideal solution is always a spontaneous formation. That means if you have two solutions, two liquid solution, two pure liquids added to form a solution, then it is always a spontaneous change. Okay, these are the examples which I explained you earlier already. So please check these conditions very, very carefully. These are all the conditions for ideal solutions. Okay, right. Obviously, identifying ideal solutions is very challenging. There will always be some deviations from the ideal solution. And we explain this as the deviations from Raoult's law. And we express them as either a positive deviation or a negative deviation. First, let's talk about positive deviation. In case if the AB interactions are lesser compared to that of individual AA interactions and BB interactions. That means the attraction between the solute and solvent particles is weaker, right? When you have only solute or when you have only solvent, the attractions are stronger. But now the attractions are weaker. Then we say there is a positive deviation. Okay. Second, it does not obey Raoult's law. When it does not obey Raoult's law, that is P total is not equal to P naught A XA plus P naught B XB. And because the interactions are weaker, the pressure of A and pressure of B, which we expect it to be equal to P naught A and XA, now it should be more because it is easily volatile. Because AB interactions are weaker, it makes both A and B to evaporate more easily. That's why the partial pressure of A, partial pressure of B, both you will find to be greater than their, normal P naught AX A and P naught B XB. One second. Right. Therefore, the P total, which is also equal to PA plus PB, that should be greater than P naught A XA plus P naught B XB. Okay. It's like we are expecting a total pressure of 1 atm, but you are getting a total pressure after measuring, you are getting something like 1.25 atm. Then we say there is a positive deviation happening. Because the interactions are weak, correct? The particles have to move more easily. To move around, they will absorb the energy from the surroundings and use that for their kinetic energy. Therefore, delta H of mixing will be greater than 0 in positive deviation. And because energy is absorbed, the particles are slightly away from each other. The overall volume of the solution will be slightly greater than the individual volume, sum of individual volumes. And delta H of mixing in any case is positive because you are mixing two solutions. So overall volume is always going to increase. So the final volume is always greater than VA or VB. So therefore delta S of mixing is greater than 0. And these are very important examples, everybody. For positive deviation, usually we should see there is a loss of some strong bonding which was already existing. For example, if at all I have ethanol, okay, ethanol have strong hydrogen bonding in its liquid state. And then you added one more liquid like hexane. Now what would happen? Between two ethanol molecules which has strong dipole moment like this, now something like an hexane will come in between, correct? And hexane is non-polar. So neither these two will make strong interactions nor these two will make strong interactions. And obviously these two are far away now because something in the middle, we have something like an hexane. So hardly much attraction will take place. Therefore, for both hexane also it is a problem, for ethanol also it is a problem. Hence, the interactions between hexane also becomes weaker and ethanol also becomes weaker. That allows them to have weaker interactions and more volatile mixture of solution. Same logic, benzene plus ethanol. And you see water and methanol or ethanol also. Okay, got it. So even if you add water, water is a, I mean, if you take water as a solvent and you add ethanol into it, correct? You will notice that the boiling point of water actually comes down. Boiling point of water is supposed to be 100 degrees. Ethanol is supposed to be 78 degrees. But if you mix in this composition, right, 95 to 5%, you can see now the boiling point is only 75 degrees. It has actually decreased. Okay, that's what you will notice, that when two liquid solutions give a positive deviation, the solution becomes more volatile and easy to boil. So at lower temperature only it will boil. Okay. Now, how do we explain this graphically? See, if it comes to positive deviation, ideally the total pressure should go like this, and ideally partial pressure should go like this. Correct? But now, because there is a positive deviation, you will see the total pressure should be greater than the ideal pressure. The partial pressure of A should be greater than the ideal partial pressure, and partial pressure of B should also be greater than the ideal partial pressure, like this. So this graph represents that the P total which you are getting right now is greater than P naught A XA plus P naught B XB. Okay. So it is not agreeing upon Raoult's law, but you can get an idea that it will be greater than what pressure it accumulates via Raoult's law. Okay. Now, importance of these liquids, most of them, I mean, it's not all of them, but yes, whenever there is a loss of hydrogen bonding. So you might ask, sir, are these the only examples? No, well, not exactly. But what if you have something like this? Let's say I have something like an acetone, and in acetone, I have added something like an hexane. Here also, acetone naturally has some polarity, delta positive and delta negative charge it has. Hexane is completely non-polar. Mixing these two will only develop a positive deviation. Correct. But in such cases, right, there is not much of a loss of bonding. But in the cases like these, there is a strong loss of hydrogen bonding. So such mixture where there is a strong loss of interactions, correct? Then we see the graphs going slightly different way. Suppose if it is only this kind of case, right, then the graph would look more like this, just like this normally. So it is a positive deviation, it is going like this. But for the cases where there is a large difference in the, I mean, there is a drastic change in their interactions, in such cases, you will see like this here. Let's say if P naught P is here, it will go like this. Okay. And this line, which is suppose, if you remember, this was the total pressure line. And um, if you remember that, its total pressure curve will also be like this uh, in terms of that mole fraction in the, this was ideal pressure P ideal as a function of mole fraction in the liquid state, correct? This is P ideal pressure as a function of mole fraction in the liquid state, correct? X is the mole fraction in the liquid state, Y is the mole fraction in the vapor state. So this is the total pressure curve for ideal. This is the total pressure curve for ideal. Okay, one with liquid composition, one with vapor composition. And this is how it should go, correct? But now what I'm saying, in cases where there is a drastic loss of bonding, then this line, this curve will go this way with some height, and then you will notice the bottom curve which was there here, this one, the ideal one which is expected. Now that will go like this. It will touch somewhere here, and then it will go and touch here. Okay. So you will see a strange phenomena happening here. That is, you are getting a certain point where the mole fraction, see here, if at all I say mole fraction, this is in liquid state. If I draw a horizontal line, this is the mole fraction in vapor state for the same liquid of the same liquid composition. Same way, if this is for liquid state, if I draw horizontal line here, that will be the vapor state composition. But now this is a point where you are actually noticing both of them are same. So this is a point where mole fraction of XA and YA will be equal, or XB and YB will be equal. Okay. Such a case where the mole fraction in liquid state and vapor state is same, then we say the mixture of the solution is called as azeotropic mixture. It is an azeotropic mixture. Okay. At which point? This point it is an azeotrope. So at this point it is called as azeotropic mixture, everybody. Clear? For example, water and ethanol forms an azeotropic mixture when it is 95% and 5%. That's why if you try to evaporate water at this composition, you will not be able to separate ethanol and water, because Both their mole fractions are same. If you condense it also, you'll get same mole fraction. If you evaporate, you'll get the same mole fraction. So it is difficult to separate these two liquids anymore. So azeotropic mixture is the case where you cannot separate the liquids by distillation. Okay. Now notice this. If this is the vapor pressure of liquid B and this is the vapor pressure of pure liquid A, which one is more volatile? I can definitely say that A is more volatile in this case and B is less volatile. Lesser the pressure, less volatility. Now tell me, the one which is more volatile, its boiling point temperature will be less. And the one which is less volatile, its boiling point temperature will be more, correct? Isn't it? So that's why for this it will be up, for this point it will be down. Okay. So now instead of pressure, if at all I plot temperature versus mole fraction, if I plot temperature versus mole fraction, then since this is down here, now the point here will be up. And this is up here, so now the point will be down here. So therefore, now if at all I draw the azeotropic line here like this, okay, then you will notice the graph would go something like this. From here, it will go all the way here and touch, and from there it will go like this. Okay, and this will be the liquid line now. This is the liquid line. Okay, and the vapor line would be going like this. Vapor curve will be going this way. Okay, this is the graph with respect to pressures. This is the graph with respect to temperatures, boiling point temperatures. So have you noticed this particular point here now? So at this point here, you're getting a certain point where this temperature is minimum. This temperature is minimum. Okay. So this is the minimum temperature at which you will get this point. Okay. So this is called as minimum boiling point temperature. Correct. So this is called minimum boiling point azeotrope. Minimum boiling point azeotrope. So for a minimum boiling point azeotrope, this is how the graph looks like. Okay. So everybody, please check it out. What is positive deviation? Let me know if you have a doubt in that. In case if AB interactions are way stronger than AA interactions and BB interactions, then we see negative deviation happening. And it does not obey Raoult's law. That is, P total should not be equal to this. Rather, now you'll notice the actual total vapor pressure of A and B are less than what it ideally should have. Okay, ideally, this is what it is expected to have as the total pressure, but the total pressure now will be less than that. So this is negative deviation. Delta H of mixing will be less than 0, and energy is released to the surroundings in this case. Because of strong interaction is happening, energy is released. And because of strong interactions, molecules will come closer and the delta V of the mixing is less than 0. I told you that irrespective of whether it is positive or negative deviation, since you are overall increasing the volume for both the individual components, delta S of mixing is greater than 0. Okay, and delta G will be less than 0. And next, if you notice the examples here those are the cases where you actually have a formation of ions or a strong hydrogen bonding being made. For example, if you add HCl to water, what will happen? HCl will split into ions. So ions will have extremely strong interaction. Because of the strong interaction, now they will act like a negatively deviating solution. Same way, any acid added to water, any base added to water. And then case like this, right? Where we have chloroform and acetone. So chloroform has weak interactions as a pure form. Acetone also has a weak interactions as a pure form. But when you mix both of them, the oxygen from acetone and hydrogen from chloroform makes a strong hydrogen bonding. Likely, phenol has a good strong hydrogen bondings. Aniline has a strong hydrogen bonding. But after mixing both of them, the hydrogen bonding developed between nitrogen and this hydrogen will be even stronger. That makes it negative deviation. So guys, if you have these kind of mixing of solutions, you would generally have a stronger interactions, making it less volatile solution. So that's why you'll see the boiling point of HNO3 generally is 110, water is 100 degrees, but now a certain mixture of this will boil at 126 degrees Celsius. So you can notice that the boiling point has increased because you will see that it is starting to show more of negative deviation. Clear on that? So notice this one. So when it comes to negative deviation, how does the graph changes? So in this case, you will see for total pressure graph, the total pressure graph will go like this because it is negatively deviating. Okay. And this is the ideal pressure. This is the P ideal, correct, which is a function of X, which is the mole fraction in liquid state. Okay. And this you can see at any particular composition, if this much is the total pressure you are expecting, actually it is only showing this much pressure. Okay, same thing, you will see the pressure of individual pressures will also be less, total pressure also will be less like this. So this is what practically observed. This will be for PB, this will be for, sorry, PA, this will be for PA, this is for PA, and this is for PB, and this is total pressure. And if I draw this in terms of temperature, boiling point temperatures here, so you will see, again, let me write down some azeotropic line here. If this is the azeotropic line here, then the graph would go something like this here. See, here it is less volatile, here it is more volatile. So less volatile temperature will always be more volatile temperature will be less. So it will go like this from here, go this way, and from here it will go towards less volatile form like this. And when it comes to the pressure temperature in terms of Y, that is mole fraction in the vapor state, this is how the graph will go. Now you are noticing that there is a maxima which is appearing, correct, where it has the maximum boiling point azeotrope. Maximum boiling point azeotrope. Okay. And at this point, you know that XA is equal to YA, XB is equal to YB. Here. So this is about negative deviation, everybody. Very similar to positive deviation in terms of those pointers. So what all you need to check out is here we'll have a stronger interactions, and in an azeotrope you will get a maximum boiling point azeotrope. You can see this is the composition of the azeotrope. This is the maximum boiling point, right? This is the actual boiling points of individual components, but this is the maximum boiling point of those components, right? Now this was about Raoult's law, everybody. Now let me introduce to the idea of what is colligative properties. See, colligative properties are generally more applicable when you have non-volatile solute, which means which will not evaporate on its own. Something which is like solid, like sugar. Sugar is non-volatile, salt is non-volatile. So if I take some sugar, urea, some starch or some salts, we take that solute, add it to a solvent which is volatile. You're adding this to a solvent, which is volatile. Correct? In that case, what would happen? You will see some properties of the liquid would change. Got it? And the change in the properties will be specifically dependent on how many number of particles of non-volatile solute you have added. Sorry, this is non-volatile solute you have added. It always depends on the amount of non-volatile solute. Such properties which vary only on the basis of amount of non-volatile solute added, those are called as colligative properties. Okay. For example, adding a teaspoon of sugar in water, correct, or a large quantity of sugar in water, these two solutions will have different types of different values of certain parameters. Those parameters are RLVP, EBP, DFP, and OP. This RLVP means relative lowering of vapor pressure, EBP elevation in the boiling point, DFP depression in the freezing point, OP osmotic pressure. These are four different colligative properties which solely dependent on how much amount of non-volatile solute you have added. Okay. Now, non-volatile solute are of two kinds. One are non-electrolytes, the other one are electrolytes. Non-electrolyte means which will not ionize in the solution. Like glucose, when you add it to water, it will dissolve, but does not mean glucose will split into ions. Sugar will dissolve but not split into ions. Urea will dissolve but not split into ions. While NaCl, KCl, KNO3, calcium nitrate, calcium carbonate, these are those non-volatile solutes which on add to the water will start ionizing completely. So you'll start seeing Na plus and Cl minus, K plus and Cl minus forming like that. Now, if you take whether a non-electrolyte or an electrolyte, it will change the properties. Now, first let us start with adding a non-electrolyte, everybody. If I add a non-electrolyte, that means either a sugar, glucose, urea, these kind of solutes. And let's say A is a solvent here and B is a solute. Solute is which one? Non-volatile, non-volatile, non-volatile solute. Okay. In that case, how do we figure out this relative lowering of vapor pressure? What is its definition? Let's see that. Okay. See. Here we know that since it is non-volatile, can I say that P naught B is equal to 0? And P naught A is non-zero because it is volatile. Okay. And we know that now the total pressure as per Raoult's law, which is supposed to be P naught A XA plus P naught B XB, since this term is completely zero, P naught B is zero, this is zero. So we'll get this as P naught A XA. So P total, right, is equal to simply P naught A and XA, where XA is the mole fraction of solvent. Mole fraction of solvent. If I write that in terms of mole fraction of solute, what would I get? I'll get this as P naught A into 1 minus XB. So which can be written as P total. I'll simply write this as P of solution. PS as in P of solution is equal to P naught of the solvent, right, minus P naught of the solvent into XB. So if I take it to the left hand side, I will get this as PS, right, sorry, P naught minus PS is equal to P naught XB, which implies XB is equal to P naught minus PS upon P naught. Okay. So P naught, in a sense, this is same as the P naught B. PS as in this is PB. PS is same as the PB here. So therefore, P naught B minus PB upon P naught B, that must be equal to, sorry, P naught A here, sorry, not, because A we took it as solvent. A. So P naught A minus PA by P naught A is equal to mole fraction of B. Okay. So now you notice that this is P naught A, which is the pure solvent vapor pressure, and this is the change in the vapor pressure relative to P naught A. That's why it is called as relative lowering of vapor pressure. So this entire term is called as relative lowering of vapor pressure. So delta P by P naught is equal to XB. This is the formula, relative lowering of vapor pressure formula, delta P by P naught. Clear everyone? Now, see, I can also write this equation in the other form, that is P naught minus PS divided by P naught, which is equal to XB, mole fraction. XB can also be written as number of moles of B by number of moles of B plus number of moles of A. Correct. So if I reverse this value, so I can write it as 1 by 1 plus, sorry, 1 by, uh, I'll do one thing, I'll just reverse and write it back again. So write it this as P naught by P naught minus Px is equal to Na plus Nb by Nb. So if I do that, I will get this as P naught by P naught minus Ps is equal to Na by Nb plus 1. So if I take this 1 to the other side, I'll get this as P naught minus P naught minus Ps, sorry, minus Ps, that divided by P naught minus Ps, that is equal to Na by Nb. Now reverse this again. So you can see P naught will get cancelled. So you can get this as P naught minus Ps upon Ps, that is equal to Na by Nb. Okay. This is another way of representing the formula, where instead of writing in terms of mole fraction of the solute, we are writing in terms of mole fraction of the ratio of the mole fractions, which is number of moles of B by number of moles of A. Got it? So this is about relative lowering of vapor pressure, everybody. Okay. So understand the definition. This itself means this ratio, this relative ratio is what we call it as the relative lowering of vapor pressure. Okay. Please go through it once quickly. If you have it out, you can ask me. Before we go further into detailing of what is elevation in the boiling point, okay, let us quickly try to understand the difference between these two terms. What is evaporation and boiling? Okay. See, evaporation only happens when on the surface particles there is an exchange of energy. It's a very slow process. It happens over a range of temperatures. It is an endothermic process where energy has been absorbed on the surface and it is helping in making the particles move away from the solute, move away from the liquid. While what is boiling? Boiling is actually a bulk phenomena. There is a exchange of heat in the bulk, not just on the surface. This process is a very rapid process. It always happens at a particular temperature. It is also endothermic in nature, and vapor pressure of the liquid, that is how much amount of pressure it is creating here, this versus the external pressure outside pressure, how much it is. If those two becomes equal, then we say the boiling phenomena has started. So then most of the liquid will convert into bubbles and those bubbles will start coming out. Okay, so that phenomena is called boiling. So this is important point to note when it comes to boiling. That is, vapor pressure of liquid should be equal to external pressure. Using Clausius-Clapeyron's equation. This is ln P2 by P1. We learned this already. This is individually how the equation looks like. The graph also explained you how does it go. So if it comes to pressure versus temperature for a volatile liquid, this is the kind of graph you will notice. Correct? Now, why I wrote these three graphs? Check it out. This is the actual graph when you have pure solvent. When you have pure solvent. Now, instead of taking pure solvent, you added some non-volatile solute. Then it has become solution now. Now, for that solution, if you start plotting the pressure, vapor pressure versus various temperatures, then you'll actually see the graph going this way now, slightly away from the pure solvent graph. And if you add more amount of solute, the graph will keep shifting onto the right hand side like this. Now, suppose if this is a P1 atm line here, this is 1 atm atmosphere, 1 atm external pressure. In that case, the point where it is meeting this graph, correct, this curve, that if you extrapolate here and check it out, this temperature T2 is the boiling point temperature of this mixture. Next, boiling point temperature of this mixture and boiling point temperature of pure liquid. So you can see if you add a non-volatile solute, the boiling point of that liquid is actually increasing. The boiling point is increasing. That's why we say it is an elevation in the boiling point. Okay, we do not. Why we use the word elevation in the boiling point is because the overall boiling point of the liquid is increasing. Got it. Now notice one thing here. If you check it out, there are two basically triangles which are forming here. Check out properly. One triangle is like this. Okay. Why triangle I'm saying? Consider for a small addition of solute particles, then these graphs will be very close by. When they are close by, you can see this is AB and this is AD and BD and AD. So you're getting an right angle triangle here like this, ABD. Okay. And similarly, you are also getting one more triangle. If your concentration is slightly increased, you'll get one more triangle like this. Okay. What is this one? ACD. You'll get this as ACD here. Okay. So you'll get ABD and ACD as these two triangles here. Correct. So in that case, if you see that almost they are linear in this region, they're almost linear in this region. So we can assume that these are the two triangles. Okay. So using the properties of triangles, we can say that, for triangle ABD and triangle ACE, okay, applying triangular properties. So it is properties of triangles. If you apply, I can say that AD by AE. Please check it out. What is AD here? This is AD and this is AE, correct? AD by AE must be equal to AB by AC, correct? Right. So what is this AD here, everybody? AD is the difference in the pressure, correct? This is the amount of difference in the pressure that was created. You're expecting this much amount of pressure, but at that temperature, you're only getting this much amount of pressure. So there is a decrement in pressure. That is what we learned, lowering of vapor pressure. So there is a decrement in pressure. So we can say that this is equal to AD represents delta P for solution 1, okay, which is equal to P naught minus P1. Similarly, AE equal to delta P for solution 2, which is equal to P naught minus P2. Okay, so if I substitute that values here, I can get this as P naught minus P1 by P naught minus P2 is equal to temperature difference. Temperature difference is AB here. So you can see this is the temperature difference, AB and AC. So AB and AC includes T1 minus TB upon T2 minus TB. This is what you will get. So which I can write it as delta TB1 by delta TB2. From here, it's evident that the change in boiling point temperature is directly proportional to relative lowering of vapor pressure. Correct? This is relative lowering of vapor pressure, delta P by P naught. And delta P by P naught, we learned this as mole fraction of solute already. So from here, I can say delta TB is directly proportional to mole fraction of solute. Mole fraction of solute. So that implies delta TB can be written as some constant A into mole fraction of solute. Okay. Let me put this as equation 1, everyone. Okay. Let me put this as equation 1. Clear? And now, uh, next, if you notice this one, when it comes to P naught by P1, 1 second, which one I can use? Right. Check this out. Now, what we can use here, we know that ln P naught by P1, which is, I'm using the Clapeyron's equation, that must be equal to delta H of vaporization, by R into 1 by T1 minus 1 by T2. T2 in this case here, it is boiling point, original boiling. Okay. T2 by T1, here it is P2 by P1, then it is T1 minus T2. So otherwise, yeah, this is correct. Clear? T1 minus T2. Now, if at all I write this down, I can get this as delta H of vaporization by R into TB minus T1 by T1 into TB. Correct? If I take the LCM on both sides, this is what I'll get. So which is equal to delta H of vaporization into this, I can write it as delta TB by T1 into T2. Okay. And since we are taking these values in a very close range, because for a very small quantity of solute we are adding, then I can say T1 and TB are very close values. So I can write this as delta H of vaporization, into delta TB upon RTB square. Correct? This is ln P naught by P1. Okay. And if you recall, you know that P naught minus P1 by P naught, that is equal to mole fraction of the solute. This is lowering of vapor pressure. Okay. And this I also wrote in terms of, um, if I write this in terms of mole fraction of the solvent, then what would I get? I can write this as 1 minus mole fraction of the solvent is equal to P naught minus P1 by P naught. I can write this P naught minus P1 by P naught. And now mole fraction of solvent can be written as P naught minus P1 by P naught. Sorry, 1 minus this entire thing. So that is P naught will get cancelled. We'll get this as P1 by P naught. So which implies I can write it as P naught by P1 is equal to 1 by mole fraction of solvent. Correct? 1 by mole fraction of solvent. Why I use this? Because this value I can directly substitute into this logarithmic value. So then I will get this as ln 1 by mole fraction of the solvent, which is equal to uh, uh, yeah, let me do one thing. 1 by x of solvent, I can write it as minus ln of x of solvent, and minus ln of x of solvent can be written as 1 minus x of solute. correct. And if you remember the logarithmic expansions, if you have log 1 minus x where x is very smaller value than 1, then this can be written as minus x. So the same thing I can write. So this will become minus of minus will become plus. So this can be written as x of solute. So can I say this? Ln 1 by x of solvent can be almost same as x of solute. So therefore, the same value, that is ln p naught by p1, which is equal to ln 1 by x of solvent, can be written as x of solute. This we can substitute back into this equation. All right. So if I substitute this back into the equation, I will get this as uh, this entire thing we got it here, right? So let me write down that x of solute, mole fraction of solute, is equal to delta H of vaporization, that is delta H of vaporization by RTB square into delta TB. This is what we got. Okay. So equating this with this one here. Right. Now, can I say that solute can be written as number of moles of mole fraction can be written of number of moles of solute by number of moles of solvent. So which can be written as number of moles of solute by number of moles of solvent can be written as weight of solvent into molecular mass of the solvent. Correct. Which can be written as number of moles of solute, number of moles of solute upon weight of solvent. This was in grams. Now I'm writing it in kgs. So if you write it in kgs, multiply that with 1000 into mole fraction, molecular weight of solvent. Now this, if I equate here and here, have you noticed something? This is the definition for molality. Hence, delta H of vaporization by RTB square into delta TB is equal to mole fraction into molecular weight of the solvent by 1000. Okay. So let me pull all of them to the other side. So I'll get this as delta H of vaporization into delta TB divided by, right, 1000 will go up, divided by RTB square. This is equal to molality. Or now I can write it as delta TB is equal to RTB square by 1000 times of delta H of vaporization into molality. Now this is what we write it as Kb as a new constant. Delta Tb is equal to Kb into molality. Correct? This Kb is called as, abelioscopic constant, abelioscopic constant or elevation constant, elevation constant. Okay. So this is the formula you will be using to figure out how much is the elevation in the boiling point. So delta TB is the amount of elevation in the boiling point and Kb is the constant value into M. So how do we find Kb? You have noticed that Kb formula is RTB square of a solvent upon, sorry, M should be there. I forgot M somewhere, I guess. Where did M go? Yeah, M is here. Sorry, M of solvent. Yeah, M of solvent here. Here it is there. M of solvent. Right, molar mass of the solvent divided by 1000 times of delta H of vaporization, everybody. Okay, so this is how you derive into the formula where Kb value can be evaluated. Correct. So is this derivation important? Not so much, just for your understanding how we use the elevation in relative lowering of vapor pressure only and Clausius-Clapeyrion's equation to eventually derive what is elevation in boiling point. Okay, so I hope all of you got this. What is delta TB and KB represent? I hope there is no doubt, everybody.